In this online lecture, we're going to talk about the second type of substituent, and that is the orthopair-directing deactivators. And if you remember from the previous online lecture, we saw that substituents can affect the reactivity of benzene, and we also remember that substituents can affect the orientation of other substituents being added to benzene. These are our really big picture points here. So let's do our analysis like we did with the first group to this second group here. And like we did with the first group, let's look at the substituents that are categorized under orthopara-directing deactivators. This group is the easiest to memorize because it's simply just all of the halogens here. And let's do our same type of analysis here like we did in the previous online lecture. We want to talk about how do these substituents make benzene more or less reactive, and where do they direct other substituents? Well, remember, it has to do with looking at both the resonance and the inductive effect. So let's look at the inductive effect that a halogen would have on a benzene ring. Remember, right here, this Br is more electronegative than this carbon. So it means the electrons in the sigma bond between the Br and the carbon would be pushed towards the Br. So that means that the Br has an inductive withdrawing effect on the benzene ring. So that takes care of that. Let's place this off to the side so we could remember that. Now let's talk about the resonance effect. Remember, we learned before that in order to study this, we need to look at an actual resonance structure. And the resonance move that we could make, at least one of them, looks like this. The electrons on the Br can fall down here, and the pi electrons in the benzene ring could jump up on top of a carbon. And again, notice the overall direction of these arrows and these electrons. They're going towards the ring away from the Br. So Br gives an additive resonance effect or donating resonance effect. And let's put this off to the side here. Now at this point you might be thinking, this was the same arrangement that we got with the first group, the orthopair-directing activators. So what's the difference? Well, here's the difference. For these types of substituents, it's the inductive effect that is more powerful than in the resonance effect. That is the exact opposite for group 1 substituents. Now, just as we talked about in the last lecture, knowing that one particular effect is stronger or more powerful than the other is not something we can determine just by looking at the substituent. The fact that in this case the inductive effect is more powerful than the resonance effect is just a fact about this substituent that was determined in the lab by running the reaction. So basically this fact is just something we have to accept and memorize. And it's always going to be true for these orthopair-directing deactivators. So what that means is, what is the overall electron movement? Well, if inductive is greater and it's pointing outward, then that means overall the Br and all halogens are electron withdrawing when they're on a benzene ring. So we would call Br an electron withdrawing group, or EWG. Now, how does this affect the reactivity of the benzene ring? Well, remember we learned in the previous online lecture that if a substituent on a benzene ring is overall electron donating, then it is an activating substituent. But that's not what we have in this case. Here, the Br is overall electron withdrawing. So if a substituent on a benzene ring is overall electron withdrawing, then it is a deactivating substituent. Now remember, don't just memorize this blindly. Let's go back. The argument we made in the previous online lecture that right here, this is the first step of electrophilic aromatic substitution. And after this step, this is the intermediate that you would get. And we said the first type of substituent is overall electron donating, which meant that that overall added electrons to this positive charge and made it less positive and therefore more stable. But now in this online lecture, we're saying the substituent is overall electron withdrawing. Pulling electrons away from a positive charge makes it even more positive and therefore less stable. So, hence the key point here, in this case, if a substituent on a benzene ring is overall electron withdrawing, then it is a deactivating substituent. So, it's important to know this truth, but it's just as important to know why, and that's why we're taking the time to discuss that here. So, let's go back to our substituent analysis here. We're now labeling the halogens as overall deactivating substituents. And that explains why in the title of this type of substituent we have the term deactivators. And I want to point something out here really quick. When we say that Br is a deactivator, we're not saying that it makes benzene not reactive. We're just saying that it makes benzene less reactive. Compared to what, you might ask? Well, compared to just benzene by itself. So it's kind of a misnomer. In all honesty, I think they could have used a better term here because deactivator might make you think not reactive at all, but careful, that's not the case. Still reactive, just not as reactive as just plain benzene. So that explains that part. Now, how do we explain the Orthopara directing? Well, we're going to do it the same way that we did with the other substituents. We react them, we add an electrophile Orthopara and meta, and see what's more favorable. So let's do that here. We're going to add the electrophile. The first step of electrophilic aromatic substitution is we grab this electrophile, and let's take care of ortho first. What we would get as our first intermediate is this molecule right here. And just like we did before, let's analyze the resonance structures that we would get. Well, the first move we could make is that these pi electrons move this way. What we end up with is this as a resulting resonance structure. And again, we can keep making that move. We can say these pi electrons move this way, and that leaves us with this resonance structure. And notice what happened here. The positive charge is on the carbon that's bearing the original Br substituent. Remember, I told you in the previous online lecture to remember that that's always going to be the case. Again, meaning that if you add an electrophile ortho to a substituent, the positive charge in one of the resonance structures will eventually land on that carbon bearing the substituent. Again, I devote a whole online lecture to this point alone and why that's so important to know. But for now, let's see if we can draw another resonance structure. And here it is. We can say the electrons on the Br fall down here, and then we end up with this resonance structure. And notice what we have here. Compared to the previous three resonance structures, this resonance structure has more bonds and therefore more octets. So guess what? You know what that means? It means he's relatively stable compared to the others. And it means that adding an electrophile ortho to a halogen, you get a pretty stable intermediate, which means it's looking like the electrophile would like to add to ortho if it had the option. So again, that's our analysis here. Let's keep track of that and put it up here. And let's remind ourselves that we do get this relatively stable intermediate. All we have to do now is quickly evaluate the meta and the para addition. So let's look at meta here. Again, first step of the mechanism is this. We're going to add meta, which means this is our first intermediate. We then look at the resonance. Again, electrons can move this way. That leads us to this as an intermediate. The next move we can make is say these pi electrons move this way, and that leaves us with this intermediate. And if you notice, there's no more moves to make here. We've exhausted all of our possibilities here. Two things to notice at this point. Number one, we're only getting 3 resonance structures compared to the 4 that we got with ortho attack. And not only that, we're not landing on that more relatively stable resonance structure. None of these structures have the positive charge on the carbon bearing the bromine. So that completes our analysis for meta attack. And again, placing him in the big picture here, we have ortho taken care of. Now we just have to do para. So let's do that here. Again, first step of the mechanism, grab the electrophile. We're going to add him para to the Br. We get this intermediate. We can draw this resonance structure right here and end up with this one. And notice right there, the positive charge is on the carbon bearing the bromine, which allows us to draw this resonance structure right here, leading us to that more relatively stable resonance structure. But if you remember, it doesn't end here. You can actually go back to this second resonance structure right here and draw a different resonance result, which means if I say these pi electrons move this way, then I would get this resonance structure right here. So notice we get the same 4 resonance structures as we do with ortho attack. So in fact, let's put it all together here, our complete analysis. Under ortho attack, we get 4 resonance structures and something relatively stable. Under meta-attack, we only get 3 resonance structures, no relatively stable structure. And for para-attack, we get the same thing that we would get with ortho-attack. So therefore, adding an electrophile to a benzene ring that has a halogen on it is going to prefer to go down either an ortho and a para pathway. So what does that mean to us? Well, sample problem right here. On your orgo test, this is what you need to do quickly. If you have this molecule and you need to decide what is the product of this reaction, remember the first thing you'll remember is that Cl and FeCl3 place a halogen on a benzene ring. But since you already have a substituent on the benzene ring, you have to ask yourself, what kind of substituent is that? Now, you'll have memorized that he is a group 2 ortho-para-directing deactivator, as in on the exam you're not going to go through this analysis to see where he adds. You simply don't have time for that. So you'll memorize that it's ortho-para-directing deactivator, which simply is telling you that the added Cl is going to add ortho to the Br. That would be one of the products we get, and the other product we would get is adding the Cl para to the Br. And again, like I mentioned in the previous online lecture, this doesn't mean that doing all the analysis is a waste of our time. Remember, typically on an orgo exam, a very good one that is, your professor might put a substituent that is not in one of these categories that you have to do the analysis and figure out what type of substituent he might be. So again, that's why we're taking the time to learn how to fully analyze a substituent. But if we already know that a substituent is in one of our categories, we're just going to call it the way we see it. So again, that means anytime you see a halogen on a benzene ring, you're going to know right away that he is an ortho-para-directing deactivator. Now, some of you might take issue with this, and let me show you what I mean by that. Think about this. We just learned in this lecture that Cl, the halogen, is an ortho-para-directing deactivator, whereas OH, in the previous online lecture, we learned that he's an ortho-para-directing activator. Which remember means that since Cl is a deactivator, it makes the ring less reactive, whereas OH is an activator, it makes the benzene ring more reactive. And we even talked about why. Remember, we said both of these structures have an additive resonance effect. This is what it would look like for the Cl, and this is what it would look like for the OH, both adding electrons to the ring. And we also made the point that the inductive effect is also the same, in the sense that, remember, since the Cl is more electronegative than the carbon, the inductive effect would be outward. And again, since the oxygen is more electronegative than the carbon, he would also have an inductive withdrawing effect. So that's the same here for both. But remember, we said that the Cl is overall electron withdrawing, whereas the OH is overall electron donating. And that was because, remember, for the Cl, the inductive effect is greater than the resonance effect. Whereas, remember, for the OH, it was the resonance effect that's greater than the inductive effect. And here's where some of you might have an issue. Think about it. Isn't oxygen more electronegative than Cl? If that's the case, then how could Cl have a greater electron withdrawing effect than OH would have? OH, being more electronegative, should withdraw electrons more strongly away from the ring than Cl. Well, let me resolve that for you here. It's really all about the resonance effect, not the inductive effect. And let me show you what I mean here. Let's tilt this molecule here, and let's look at the resonance effect. Remember, that means drawing this resonance structure right here, we end up with this result. We get that new pi bond right here. And remember, a pi bond by definition is a sideways overlapping of p orbitals. So let's think about the orbitals here. This oxygen would have a 2p orbital, and the carbon right here would also have a 2p orbital. So when this pi bond forms, the 2p orbitals on each atom would sideways overlap and make this bond right here. Since these two orbitals are the same size, we get maximum overlap, which means that contributes to a very powerful donating resonance effect. Let's do the same type of analysis, but with the halogen now. Again, doing his resonance move, we get this right here, and also again we get a pi bond being formed. But what would be the 2p orbitals that sideways overlap to make this pi bond? Well, think about it. For the Cl, it would have to be his 3p orbital. How do I know that? Well, remember, going back to the periodic table of elements here, remember chlorine is in the p block. he is on level 3 here, so that means he has 3 p orbitals. Not 3 in number, but 3 in size, as in 3 units away from the nucleus. Whereas oxygen right here would have 2 p orbitals, again, not in number, but in distance and size. Notice oxygen is at the same level of carbon. That's why the pi bond between the carbon and oxygen are both 2 p orbitals. So going back to our situation here, remember, the carbon would have a 2 p orbital. When these orbitals go to overlap, they're going to have less overlap because they're not equal in size. What that simply means is a less donating resonance effect. So what that means, going back here, it means both the Cl and the OH have a very powerful withdrawing inductive effect, and the OH might even be a little bit greater. But the donating resonance effect for the oxygen is much greater than the donating resonance effect for the Cl. So that's why overall halogens withdraw electrons from a benzene ring, and OHs overall donate electrons to a benzene ring. So we're not violating any important chemistry and organic chemistry principles. So there it is. The second type of substituent. We did our analysis, we now know how to handle them, and we even got more practice in analyzing substituents.